afternoon, friends. I feel immense pleasure to come here again for my course, Aircraft Stability and Control. Today, I am in lecture number 51. This is the tutorial number 11. Topic of this tutorial is numerical problems on the perturbed derivatives. As you know, my name is Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. For this course, we have started with the module 1, which is longitudinal static stability. In that, we have discussed about the longitudinal criteria for static stability. That is, the Cm naught should be greater than 0 and Cm alpha should be negative or less than 0. If we are able to meet these two conditions, we can say that aircraft is longitudinal static stability. Also, we have worked and we have seen that the effect of different components of the aircraft like wing, tail, engine, fuselage, canard, and so on. We have derived the equations for pitching moment or pitching moment coefficient Cm, and we have seen the contribution of wing is most of the time is unstable, means it gives a positive pitching moment or clockwise moment. To counter this action of the wing, we need another small wing which is far behind from the center of gravity, so that the size of horizontal tail or the area or the volume of that horizontal tail can be reduced, so that with a minimum weight we are able to counter the clockwise moment which is created by wing. We have also seen the effect of wing setting angle, effect of tail setting angle IT, and wing is IW. And also we have seen the downwash and how this downwash is affecting on tail. In this module, we also have seen the deflection of elevator and how a trim condition of elevator can be achieved with different neutral point, static margin, and so on. In next module, we have seen that the lateral and directional static stability. In that, the vertical fin or the vertical stabilizer is the major component which is used for the directional stability. Also, the wing shape, it is higher winger, lower winger, or wing sweep, and some other geometrical parameters of the aircrafts are used, and we have seen the effect of this dihedral, anhedral, and so many things. These are making lateral and directional stability of the aircraft. Then in the third module, we have seen the equations of motion, how we have derived, and the 6 equations of motion. And the next module 4, we have seen that how we can solve the equations of motion by using the perturbation theory. In this respect, I am here for the lecture number 51, which is related to some problems. I am going to handle some 5 to 6 problems, and these problems are related to the perturbation theory, and in this some derivatives are used, and we will see that how these derivatives are giving a very good physics of the aircraft. It will be very interesting that with a small perturbation, how we can get the different forces and different moments and their derivatives. So these things I am going to discuss. In today's lecture, I am planning to first review on perturbed equations of motion, and then linearization of equations of motion. Then we will see numericals on perturbed derivatives, stability of the aircraft. By this, we are going to answer some questions in this lecture. What is speed derivative? Means u, x direction of the velocity. So what is that speed derivative, and how this damping derivatives, these derivatives we will be seeing. How the direction of the derivative determines the forces and moments. So it is purely a physics. Understanding the mathematics is one part, but understanding after mathematics how this physics will behave is very important. So it will be really very interesting to see that the whatever results we are getting and how these results can be analyzed and evaluated. You know that the Bloom's taxonomy, the students should have a higher level of understanding, especially the engineering students. And this course mostly comes in 5th or 6th semester. So all students should have a high level of understanding. So if you see the Bloom's taxonomy, in this we have lowest level is remember, then second lower is the understand, then apply, then analyze, evaluate, and then create. So as BTech student, you should be in the level of minimum apply, analyze, and evaluate. So apply is okay, because if you use the equations and you put some values, you will get the solution or some answer. And after this answer, whether you are able to analyze or not, that is the very important criteria. And in these numericals, I am going to discuss how you can analyze your problem if the results are given. So we have seen in our module 3 that we have 6 equations of motion. And if we talk about longitudinal equations of motion, this you can see here. This is the 1, this is the 2, and this is the 3. If you see, this is the 4, this is the 5, and this is the 6th equation. These 3 equations, if you see, m u dot plus qw minus rv is equal to minus mg sine theta plus fax plus ftx, where u dot is an acceleration. This is what? It is a ma. This all terms are a, acceleration. M into a is equal to minus mg sine theta plus fax plus ftx, where fa indicates a aerodynamic forces and t indicates the thrust forces. And here it is a m into acceleration. Same way for the, because in longitudinal we have the 2 forces. One is x force, that is the equation 1. Then we have the z force, equation 3. And this is the moment, that is pitching moment, that is the equation 2. Okay, so this we are going to handle, and you will see that these equations, solving these equations are very difficult, and it is a differential equations, and we will try to make it very simple so that this can be applied taking some valuable assumptions. And so now if you talk about the lateral and directional equations of motion, in this we have, first one is rolling moment, then side force equation, this is the 4th one, this is the 5th one, and this is the yawing moment equation, yawing moment or z direction. Okay, so these 3, okay, so these are the 6 equations which we have already derived, we have already discussed a lot. Now these equations are very difficult to solve. So next, our we have to make these equations in a linearized form. And if you see the linearized form, the longitudinal linearized equations of motion, again, our equation number 1 is made linearized like this. This is the equation number 2, and this is the equation number 3. This is the equation number 4. This is the equation number 5, and this is the equation number 6. So, same we have made the linearized equations of motion using the perturbation theory. If you see here, all these small values, if you see the previous one, here it is a capital U. Okay, now this capital is made in a small u, and this small u dot is a perturbed acceleration. It is a very, very small quantity compared to the capital U. Okay, so here we have made this small assumption, and we have solved and we have derived already in our previous classes. It is just only for revision here. I have mentioned here so that if we go directly for the solving the equation, solving the numericals, it will be somewhat problem, and it will be somewhat difficult to understand. So, like here Q, this is also perturbed one, V is also perturbed one, small r is, all small letters are here. These are the perturbed quantities. Here also F is also perturbed, and this Ft is also perturbed. Here also if you see this Q is also perturbed, R, P, this, and this all are the longitudinal linearized equation of motion. And you know the longitudinal means. What is the meaning of longitudinal? Just I will show you here. Once we talk about the longitudinal aircraft static stability, so the motion in X, this is X and this is the Z. If the motion is taking in a X plane, XZ plane, so this is XZ. So it may go forward or rear, that is the X. It may go up and down, it is called plunging, and in pitching. This is the Y, and it is moving in Y, X and Z plane. So this is with respect to the Y axis or the lateral axis. So these three motions, again I am just telling, X direction motion, positive, Z direction, positive Z, and pitching in lateral axis. This is called the pitching. These three motions, and as per this, these three equations are given for longitudinal linearized equation of motion in perturbed quantity. It is given like this. Same way for lateral and directional equations of motion, it is also in the perturbed way, and this we can solve very easily, and that is why we have made this linearized equations of motion so that it is very easy to solve this equation. Okay, so here PQR are the pitch rate, rolling rate and yawing rate. UVW are the velocities in X direction, Y direction and the Z direction. IXX, these all are the moment of inertia in X axis, and IXZ is a moment of inertia in XZ. So wherever I is there, I indicates for the moment of inertia, and the subscript XX with respect to the XX axis. Like this we have to understand. Now these equations further are simplified, and this is called the simplified linearized equations of motion. And here if you see mu dot, that is the acceleration in X direction. Okay, so it is a max. This is max is equal to minus mg theta cos theta 1 plus fax ftx. This theta 1 is what? Steady state condition. Wherever one subscript is there, here, everywhere, if one is there, it means it indicates that it is a pitch angle with a steady state condition. So this is the first equation here. This is mu dot is equal to minus mg theta cos theta 1 plus fax plus ftx is the first equation, second equation, and this is the third equation. And here also for the lateral and directional, this is the first, this is the second, and this is the third. So these are the simplified equations of motion, and in our previous classes we have discussed very clearly, and we have derived these equations, but only for the refreshment or revisiting or revision purpose I have here shown these all things. Here a very important things, if we take some assumptions, these equations of motions are achieved or derived using assuming wing level. So if the wing are in the level, then there will not be any phi. Trimmed and straight and level flight or steady state flight. So in this condition, if you see, there is a wing level means no rolling. So this phi 1 will be 0, pitching will be 0, yawing will be 0, all beta, this side slip, all will be 0. This we have made. And also, if we take the stability axis, body stability axis, so there will be V1 and W1, this will be 0. Means there will not be, so what is this body axis? If body fixed stability axis. So if the aircraft is flying with a body axis XB, YB and ZB, and here is the flow like this. This is the angle of attack. If you make this XB to match this XS stability axis, then what will happen? There will not be any velocity in this V1 direction, and there will not be any velocity in vertical, because the flow is parallel to the direction of the flight. So only U velocity will be there, means velocity in the direction of the flow. But the sidewise V1 and the vertical downwards velocity all will be 0. So these assumptions we have taken, and this is very good assumption. We can see further that how these things are useful for the solving the problems of the aircraft. So this we can see here. The first problem, I am just coming for that. Find U by U1 derivatives of dFAX by dou U by U1 for F4C aircraft at 35,000 feet and Mach number of 0.9. The conditions are given that U1 is equal to 876 feet per second. Q bar, it is a dynamic pressure. It is 283.2 pounds per foot square. The area of the wing S is equal to 530 feet square. If CD1, this is the coefficient of drag for steady state condition. If CD1 is equal to 0.03 and CDU, it is a dCd by du. So dCd by du means change of coefficient of drag with change in velocity. This derivative is CDU is equal to 0.027. Now, previously this U1 in steady state is equal to 876, but if U is perturbed to 880 feet per second, means it was in 876, now the speed is increased to 880. It means 4 feet per second. If you increase the speed, find the perturbed applied aero forces along the X stability axis FAX. I think the question is very much clear. I will again first explain the question. We have to find out U by U1 derivative, and this is the force derivative in X direction, dou FAX by dou U by U1, where the Mach number is 0.9. In this Mach number, the speed of the aircraft U1 at steady state is 876 feet per second. Dynamic pressure Q is equal to 283.2. Area of the wing is 530 feet square. If CD1 is equal to, the drag is this and CDU is equal to this, and we have increased the speed from 876 to 800 feet per second. So what will be the force in x direction? New force in x direction, that we have to find out. Okay, so I am proceeding with the solution of the problem, and you will see that the solution is very simple. We know the derivative for perturbed motion, that is dou fax by dou u by u1 is equal to minus cdu plus 2cd1 q1 into s. q1 into s. So this is the equation, and we have to find out this. This we have to find out. We have to find out this derivative. As per problem. So we know that from this equation that dou fax by dou u by u1 is equal to minus cdu plus 2cd1 q1 into s. cdu is given, cd1 is given, q1 not given directly, area is given. So this is not given. So what is the q1? q1 is equal to half rho u1 square. Okay, so half into 1.225 into velocity is given here, that u1 is equal to 876. So 876. So this you will get 283.2. This you will get here. So here this value is put here. So we see that minus CDU is given. CDU is given as a 0.027 and CDI or CD1 is given 0.03. These values are given here. So we can find out directly. It is very simple, that minus CDU plus 2CD1 Q1S. So here minus 0.07 plus 2 into 0.03 into 283.2, and this area is 530. Okay, so this is in FPS system. Okay, so derivative is then dFAX by du by u1 is equal to minus 13,058.4 pound. This we have got here. So what does it says? Means the slope of this derivative is, if I draw this like this, dFAX and here u by u1, so slope is like this because it is a minus. Okay, so it is given like this. So we got this derivative. So how much force we required? We have to find out FAX, means perturbed force. Means once you have changed from 880, the new velocity, and previously it was 876, means 4 feet per second u, the small u we have increased. So what we are going to get the velocity. So this velocity is very small comparing to 880. So it is a perturbed. This is called the perturbed velocity 400 feet per second. To find FAX, we have to first find out the perturbed velocity u. So how to find out this perturbed velocity u? Final velocity, this is the final velocity. Final velocity minus steady state velocity. So Final is 880 minus 876. So we got this 404 feet per second, and this is the small perturbed velocity. Perturbed x velocity. It is called u. So in this way, we can find out the perturbed velocity. If the final velocity and the steady state is given, then we can get this velocity, and it is very simple. Now, for only a u perturbed case, we are not considering v and w. Only for a u perturbed velocity, this is the u perturbed velocity, force equation Fax is equal to dou Fax by dou u by u1, which we have got it, and now u by u1. We know this u is 4 meter pound per second, and this is 876 feet per second. This, we know all the things, and this also we have got. This slope of this curve we have got as a minus. So now Fax is equal to dou Fax by dou u by u1 in bracket u by u1, and we have got this value minus 13058.4, 4 by 876. So this force we will get minus 59.6. What is the meaning of minus? You see, here I want to explain the analysis of the result. We got the result that Fax is equal to minus 59.6 pounds. But what is the meaning? That meaning we have to understand. That is the job of engineer. Not only just getting the numbers, but you don't know the things. Understand the meaning of that force. Understand the meaning of the result which we have got. Here we got Fax is equal to minus 59.6. And here Fax is a perturbed force. Means aircraft is flying with some velocity 876 feet per second. All of a sudden one gust came and 4 meter per second has increased. Now it has, the speed has become 880 feet per second. So there is only 4 feet per second velocity is increased. But you know that 59.6 pound of the force is generating. And this force is minus in x direction. So what is the plus? If you see here, this is the towards the nose. This is the plus x, and this is the minus x towards the tail. It is a minus x. So it means 59.6. It is pulling like this. It is a drag. 59.6 pounds of drag is generated only by 4 meter per second or 4 feet per second of the velocity increase. A tremendous amount of forces which are dragging by aircraft. That we have to understand. The results are very, very prompt, and it should be very much illustrated. And why? Because Fax is positive along x direction. Okay, so we have assumed that if it is towards the nose, this side is a positive, this side is negative. So this, we have predicted a 59.6 pound increase in the drag. So this aircraft, this is increased, this red pen, it is showing that this is trying to pull by 59.6. So how much thrust also required? We need more thrust to counter this 59.6. So only by increase of 4 meter per second or 4 feet per second, we need to give 59 pounds of force by the engine. That fuel consumption will also increase. Power also need to be generated. More thrust will be generated. More fuel will be given to the combustion chamber of the aircraft, or the more high rotation of the propeller has to be given to achieve this thrust. Due to this, there may be some other complications like interference of the fuselage, interference of the wings, tail and all. Okay, so not only this 59.6 pounds of the forces, but this will increase lot of fuel consumption, and it will also, if the consumptions of fuel is more, the fuel will generate so much pollution. This carbon monoxide, some other pollutants will be in the atmosphere, and you know that if the aircraft is giving the pollution directly, it is very near to the ozone layer, and the ozone layer will be lot of deflection or depleting the ozone layer. So we have to analyze these all things. As an engineer, as a designer of aeronautics, we should make sure that our ethics, our nature, our environment, everything has to be protected by your design. So we have to ensure that these types of phenomena should be reduced. So this is the conclusion. This is the results and analysis and evaluation of this result which we have calculated by this application. So we have understand the remembering. If we are able to write the formula, it is remembering. Then understand each term of the formula. Then apply means putting the value, it is applied. Then we have to do the analysis which we have done, and then evaluate further. Okay, and then if you want to make further design changes so that this 59.6 pound which we have generated by this perturbation of 4 feet per second, that can be avoided. So some changes in the wing, fuselage, tail, fin, we have to do that. This type of issue can be solved. Okay, so now my first numerical is solved. I want to go for the second numerical, and it is also very interesting. We will see that how this another problem can be solved. And in the previous one we have done the u derivatives, but now we will go for the alpha derivative. And these all problems which we have, these all equations we have derived in my module 3 or module 4. We have done it. Only just I will take on again. Okay, so here find the alpha derivatives of dfaz by d alpha for the F4C aircraft at the same flight condition as in the previous numerical one. I have mentioned here this area of the wing, Q and all these things I have mentioned. Or if you want to see this, we can see there all the speeds and other things are given there. Here CL alpha is equal to 3.75 per radian. If the 4C is trimmed at an angle of attack 2.6 degree, it is a alpha 1. Alpha 1 is 2.6 degree, and then it is perturbed to 3.1 degree. It is the final angle of attack is 3.1 alpha. Alpha is 3.1 and alpha 1 is 2.6. So 3.1 minus 2.6. So it is approximately 0.5 degree of perturbation is given. Find the perturbed aero force along the Z stability axis. So in this, we have made the aircraft is flying, wind has come. In the previous example, we have given some extra speed, the x velocity u, we have introduced some additional. In this, we have made some additional angle of attack. Previously, it was 2.6. Due to some perturbation, it is now 3.1. Little change, angle of attack has increased from 2.6 to 3.1. Then what will be the aero forces in the Z stability axis? This is the Z. So, vertical forces. What are the vertical forces that we have to find out? So, this is our aim, that if we disturb the aircraft in the, or we give some intentional perturbation of very minor 0.5 degree angle of attack, increase or decrease, it can be anything. So, what will happen on the Z forces is how much variation in Z forces will happen. So that is the problem. And the wing area is 530 feet square. It is already as the previous one, and all the speeds and other parameters are also same as in the previous one. We can see here that solution of this numerical number 2, starting with alpha derivative equation. We know that dfaz by d alpha is equal to minus cl alpha plus cd1 qns. You know that q1 we have calculated already. This one, half rho v square. Rho v is already given there, so we have to u1 here. Okay, so this area is also s is also given here. Cl alpha is given. Cl alpha is given 3.75, and here cd1 is given 0.03. These are given. So now we know this equation that dfz by d alpha, this is the slope of the curve. Okay, it is a derivative. This first we have to find out this derivative. So minus cl alpha cd1 q1s. So minus cl alpha is equal to 3.75 plus cd1 is equal to 0.03 multiplied by 283.2 into 530. If you multiply, you will get dfaz by d alpha is equal to minus 567,363. Okay, 567,360 pounds per radian. This we got. Means per radian angle deflection, this much pounds of load is generated in minus direction, minus z direction. I think you all are aware what is the meaning of minus z and what is the meaning of plus z. So now we have to find out a perturbed FAZ. We first find the perturbed angle of attack. Okay, so perturbed angle of attack alpha cap is equal to alpha minus alpha 1. So this is the final one, this is the final one, and this is the steady state. So final one is 3.1 degree minus 2.6 degree is equal to 0.5 degree divided by 57.3. You will get is in radian. So this value you will get in radian, because here we are getting in radian. So this value also should be in radian. You have to ensure that all are in the same units. So now only for alpha perturbation, we know that FAZ is equal to this dFAZ by d alpha into alpha. Okay, so this is the alpha. So minus 567,387 into 0.00875. So this we have got minus 4,951 pounds. This much FAZ we got. I think you are sure that what is the meaning of FZ minus. If I make the aircraft like this, now I am going to up to level 3. Apply you have done here. Up to level 3 of knowledge you have got up to here. But now I want to do analysis of this. Analysis, this is the 4th level. And then evaluate is 5th level. So how we can make this result in this level? Analysis. Analysis means it is a minus 4,951 pounds. So what does it mean? It means once aircraft is flying, initially it is this is the angle of attack, alpha 1. You have given some more, this is the alpha. This is a perturb, this is the alpha cap, perturb. So this perturb alpha cap is equal to alpha minus alpha 1. Alpha is 3.1 minus 2.6 degree. So you will get 0.5 degree. So if you have perturbed this much, a very small quantity, then minus 4,951 pounds of force will be generating. A very huge. A very, very huge amount of force will be generating. You can You can see, and it is a minus. So what is meaning? We have seen that towards the earth is a positive Z, but opposite to that upward, it is a force which is acting upward, it is a lift. So by 0.5 degree angle of attack change, you are getting 4,951 pounds of forces upward. It is, you are getting the lift that much. So that is the meaning of, because Fz is a positive along the positive Z stability axis. We have predicted a 4,951 pounds increase in the lift of the aircraft if the angle of attack perturbed by 1/2 degree. This may seems very large. So now we have to do the evaluating. We may feel it is very, very large. For more than 8 tons of some nearly 2 tons of lift, it is generating in upward direction like this. But how it is happening? It is happening due to the velocity. Velocity is very high, 0.9 Mach. Okay, so it is nearly somewhere 300 meter per second or nearly 1,000 kilometers per hour. Aircraft is flying in that speed. If you make a small 0.1 degree angle of attack, that much lift it will try to make upward. Sometimes we don't need this. So we have to now evaluate what factors we have to change during that condition. What pilot has to do. Which type of control pilot has to change. Like this, we have to try to find out and try to do the things. So now I will go for the numerical number 3. Find the alpha dot C by 2U1 derivatives and dma by d alpha dot C bar by 2U1 for the 4C at the same condition as numerical 1. C bar for this is 16 feet and Cm alpha is minus 1.3 per radian. If alpha dot is 0.5 degree per second, find the perturbed pitching moment Ma. We have to find out Ma now, and all the conditions are given. So we know that alpha derivative of the moment is given by dou Ma by dou alpha dot C bar by 2U1 is equal to Cm alpha dot Q1 S C bar. Cm alpha dot is dCm by d alpha dot. Q1 is a dynamic pressure, S is area, and C bar is the mean aerodynamic chord. Putting this value in this equation, so we will get here dma by this things, and here we will put Cm alpha Q1 SC bar. Cm alpha is given minus 1.3. You know that if it is a minus, it is a stable. So minus 1.3, 283.2, it is a Q1. Then S is here. Then C bar is here. All things are given. So you will get here minus 3121997 feet pound per radian. This much derivative in negative we got. Now if you want to find out the MA, moment, perturbed moment. What is the moment? It is a perturbed. It is a perturbed moment if we have given a very small changes in alpha. Due to change in alpha dot, how much moment we are going to get. So this Ma is equal to dou Ma by dou alpha dot C bar by 2U1 into alpha dot C by 2U1. So now putting this all value here, we got here, just you can see, this is this value. Alpha dot is 0.5 divided by 57.3 because this alpha dot is given 0.5 degree. This degree, if you want to convert to radian, we have to divide by 57.3. So 0.5 by 57.3, this alpha dot, C bar is 16 divided by 2 into 876. This is a U1. Always you have to take the U1, not the final value. Final value was given U is 880. But we are not taking this. We are taking only the initial steady state condition. So we got here MA is equal to minus 248.8 feet pound. That much moment we will get. It is a huge amount. Okay, so by changing a small variation or 0.5 degree, we are getting this much moment. So if you take this aircraft, this is the CG and here is your tail. You are getting like this, and this value is minus 248.8 feet pound. This much moment, and this is called the MA. This much MA you are going to get by varying a very small amount of rate of change of rate of angle of attack. So it will change the things. Now notice that degree per seconds are converted to radian per second to maintain consistent units. We have predicted a nose down pitching moment of 248.8 feet per pound, resulting from a positive 0.8 degree per second of alpha dot. Okay, so this you can see that this means it is a nose down. It is what? Nose down. Aircraft is stable? Yes, aircraft is stable, but it is making nose down. So a very small amount of change in angle of attack may change a huge amount of moment or pitching arm. So now I am going for some illustration of change in angle of attack at horizontal tail. This you can see here that if this is the horizontal tail and it is a negative, it is going down with QXH. So this QXH and this is the velocity U1. So you will get a change in angle of attack alpha H. So delta alpha H is equal to tan inverse QXH, this vertical by U1, QXH by U1, and the coefficient of lift by this CL alpha H into delta alpha H, and we are putting this value for the delta alpha H. So this delta CL is equal to CL alpha H into QXH by U1 into neta H SH by S. It is for the whole aircraft. This is for the whole aircraft. So now CLQ means DCL by DQC by 2U1. So delta CL by delta QC by 2U1. So delta CL we will put this whole value. So we will get here 2CL alpha H XH by C bar neta H SH by S. This will be 2CL alpha H NH into VH. It is a tail volume ratio. So CLQ, if we get the CLQ, we can get DMA by DQ. So it is, you will get here CMQ. So we are going to find out this CMQ. And what is this? It is called the pitch damping derivative. It is called pitch damping derivative. CMQ results from the same increase in horizontal tail lift because of pitch rate as was discussed for CLQ. So this simply multiplied by the non-dimensional moment of XH by C bar, and a negative sign is added to indicate that a positive pitch rate results in a nose down negative pitching moment. So if the nose down is there, so this nose down pitching moment, a negative sign will be there. So CMQ is equal to minus 2CL alpha H NH VH XH by C. CMQ is called the pitch damping derivative. It is a very important factor for longitudinal dynamic stability characteristics. It is negative, providing a moment that opposes the direction of the pitch rate, and will be primary factor along with CM alpha for damping out pitch oscillation. So now I am going for the next numerical. Find the QC by 2U1 derivative for the 4C aircraft at the same flight condition as in the example. CLQ is equal to 1.8. If Q is 2.5 degree per second, find the perturbed aeroforce along the Z stability axis. So in this, CLQ is equal and Q is 2.5 degree. These parameters are given. So starting with dFAZ by dou QC by 2U1 is equal to minus CLQ Q1S. So here minus CLQ, so minus CLQ is given 1.8, Q is equal to 183.2 and 538. So we got here dFAZ by dQC by 2U1 is equal to minus 270, 172.5 pounds per radian. So now we have to find out FAZ. So FAZ is equal to dFAZ by dQC by U1, QC by 2U1. So here we got this value. This value we have shifted here, and Q value is given 2.5 divided by 57.3, making this degree into radian, into C is 16, 2 by 876. So we got this value minus 107.7 pounds. So this FAZ, so this FAZ we got minus 107.7 pound. So what is meaning? It is also a lift force. If you change the Q 2.5 per degree, then you will get a lift force of upward 107.7 pound. So that is the meaning of this results and analysis. Notice that degree per seconds are converted to the radian per second to maintain the consistent unit, because FAZ is positive along the positive Z stability axis. We have predicted a 107.7 pound increase in lift if pitch rate perturbed by 2.5 degree per second. So if you perturb by 2.5 degree per second, the lift force of nearly 108 pound will be increased. So that is the meaning of this results and discussion. Now estimate the next problem, numerical number 5. Estimate the pitch damping derivative, that is called the CMQ, for an aircraft with the following characteristics. So here CL alpha H is given 0.075 per degree, neta H is equal to 0.98, VH is equal to 0.375, XH by C bar is 3. So what is here? Neta H is equal to what? It is a ratio of dynamic pressure at horizontal tail to the dynamic pressure of the wing. VH is equal to, it is a horizontal tail ratio. It is a SH into LH divided by S into C bar. It is called the tail volume ratio. And XH by C bar is equal to 3.0. Means the distance of XH, which is here, this XH. So from here CG, so this is XH. And here if this is the C, so this XH by C bar, this is given as a 3. And here DCL by D alpha H is equal to 0.075 per degree. These things are given. So we have to see that how to solve this problem. And these problems are very simple. We should try to solve these things very easily. So here we know that starting with the equation, that is the Cm alpha is equal to 2Cl alpha NH VH XH by C bar. So here minus 2 Cl is given 0.075 NH into 57.3, NH is equal to 0.98, then 0.375 into 3. So we got here CMQ. This is the CMQ. Okay, so this CMQ is equal to minus 9.48 per radian. Notice that CL alpha H has been converted to the radian. So we got that CMQ is equal to minus 9.48. So what is the meaning of this CM cube? Okay, so just I will put here this tail. This is the CG. If you are going nose up, positive M, if you give, this will go down, wing will go down, the resultant velocity will go up. Okay, so it is going down, but this velocity will generate a lift and this will make. So this moment M1 and this moment M2. So M1 plus minus M2 is equal to 0, or M1 is equal to M2, then it is a equilibrium. It is in a equilibrium condition and it is stable. Okay, so this minus indicate that it is in the opposite direction of the motion of this tail. So if it is tail is going down like this, wind will go upward and this wind will generate a lift delta LH. This LH into this distance XH. So this L delta LH into XH, this has to be countered by M1. Okay, so and it is very useful parameter for the dynamic stability. It is not only the static stability, these all parameters are handled by the for the static stability. Okay, so thank you very much for joining this class. Hope you all have understood the concept of my perturbation theory and how this small amount of perturbation may cause huge amount of forces at the moment. You have seen that at 0.9 Mach flight, if you change a 4 meter per second speed, out of 1000 or 800 meter, if you change, it is very minor, but it is not minor. It gives a lot of forces, lot of things on the aircraft, and this will give a huge amount of forces and movement. So we as an engineer, we should understand this concept and how, in case of emergency, how to handle this type of situation. Thank you very much for the joining. Be tuned for the next classes. And if you have any problem, my email is given here and my WhatsApp number. You are welcome to discuss with me in this topic. I always feel very happy to do so. Thank you very much for all.
Like, share and subscribe. Hit the bell icon for more updates.